Okay, we'll learn about the Winkler method. Now, before we talk about Winkler method, let us understand what exactly is the story behind this method. Why do we use it? When do we use it? What is the purpose of Winkler method? So, Winkler method is used to check the quality of a water body, a pond or a lake. Okay? So let's say this is a pond or a lake, and we want to check the quality of the water here. That how good is this water for the life in it. So one way to check the quality of water is its oxygen consumption. Okay, how much is the demand for oxygen in of that water body? A good quality water body should have least no, as less oxygen demand as possible. When I'm saying demand, I'm actually talking about the the dissolved oxygen available, and the more oxygen that is dissolved, the more oxygen that it obtains, and the oxygen that is consumed, which means demand and the supply. So water body will have its own resources or sources for oxygen release, which means it will gain oxygen from some sources, and there are some sources in which that oxygen will be consumed. So we just need to compare this demand and supply. So we can talk about the demand, that how much is the need of that water body. So this demand is called as BOD. It stands for biochemical oxygen demand, or even biological oxygen demand. Okay, now how do I check the demand of oxygen in this water body? That depends on the amount of microorganisms present in that water body. Okay, so in order to check the BOD, what we do is that we take a sample of water, two portions, sample we take. One portion we analyze on, let's say, today. So today is, let's say, 27th of Feb. Okay, so today will be counted as day 0. So we will analyze what is the oxygen concentration in that water. Okay, concentration of oxygen in that water. And then we wait for 5 days. On day 5, we again do the same thing. We take the second portion of the sample and we check what is the oxygen concentration present in that. So obviously both the samples were taken on the same day. So the initial concentration of on day 0 will be same. So sample 1 may I checked how much is the concentration. So this will tell me on day 0 what is the oxygen concentration. Over the period of 5 days, some oxygen has been consumed, and whatever is the concentration of day 5 and day 0, like the difference between these two will give me how much is the oxygen consumed during the 5 days. So drop in the oxygen concentration will give me the idea of how much is the oxygen consumed in the 5 days, and that's what we call it as demand for oxygen. The oxygen consumed in these 5 days is the demand for oxygen, and that we label as BOD. Now BOD is basically how much oxygen is consumed, or what is the drop in the concentration of oxygen over the period of 5 days. So this is often expressed in ppm, that's parts per million. Okay, and you need to express your answer in ppm, but understand that ppm and milligram per decimeter cube is same. Like if you want to, if you like generally the concentration units are mole per decimeter cube. So from mole per decimeter cube, if you have to convert into ppm, mole per decimeter cube ppm, you just convert the mole per decimeter cube to milligram per decimeter cube, and milligram per decimeter cube and the ppm is same. So suppose that if it's the answer is 2 ppm, so that's equivalent to the 2 milligram per decimeter cube. Okay. Anyways, we'll see the calculation part later. So so the task right now is to determine the concentration of oxygen on day 0 and on day 5. So the question is that how do I determine the concentration of oxygen in that water sample? Okay, so for that you need to carry out a few reactions, and one of the reaction is titration. In fact, the last reaction, there are three reactions that you need to carry out. The third reaction is the titration equation. So we'll just see the equations. Okay, we'll see the three steps that you carry out, and then after that we'll straight go for the calculations. So first, the sample that you have of water on day 0, you add manganese sulfate in alkaline medium. So manganese sulfate may Mn2 plus and alkaline medium is so OH minus. So this is what you add to that. So the oxygen in the sample, okay, the oxygen in the sample, in the water sample, will oxidize Mn2 plus to MnO2. Okay, it will oxidize Mn2 plus to MnO2. This is step 1. In the step 2, then you add acidified iodide ions. So acidified, so H plus, and iodide ions, I minus. Okay, and then that will reduce the MnO2 back to Mn2 plus. Okay, so oxygen in the water sample, whatever oxygen is present, has converted Mn2 plus to MnO2, and iodide, acidified iodide will convert MnO2 back to Mn2 plus. And here, iodide has become iodine. So in other words, the MnO2 has oxidized iodide. Okay, so the oxygen in the water sample has converted Mn2 plus is oxidized by oxygen to MnO2. Okay, and then in the step 2, MnO2 will oxidize iodide to iodine. Okay. Now then this iodine is titrated with sodium thiosulfate. The iodine is titrated with sodium thiosulfate. Okay, and sodium thiosulfate is in the burette. And the iodine solution that you get in the step 2, along with the other ingredients, of course, is in the conical flask. And you add that starch indicator and all. So basically, you find out that what is the number of moles of sodium thiosulfate required to react all the iodine, matlab, to convert all the iodine to iodide. And that's when the that you can get from the burette reading. Okay, so this is the volume of thiosulfate used, and concentration of thiosulfate is already known because it's a standard solution. So from volume of thiosulfate, S2O32 minus, and the concentration of thiosulfate, you come to know what is the number of thiosulfate used. Now, suppose that assume that the number of moles of thiosulfate is 4 moles. Suppose this is 4 moles. Then what is the number of moles of iodine according to the equation?
2.
2 moles, which means the iodine produced here is 2 moles because the same iodine is reacting here, right?
Yeah.
Okay. Now, if iodine is 2 moles, what is the number of moles of MnO2 then?
2.
2 moles of MnO2. Okay. So, and this MnO2 is present in the previous equation, previous reaction. And if suppose this MnO2 is 2.2 moles, so what is the number of moles of oxygen then?
1 mole.
1 mole. Okay. So you may notice that in the titration, I will find the number of moles of thiosulfate, which I started with 4 moles, and I ended up 1 mole here. So basically, I want to find the number of moles of oxygen. Okay, but number of moles of oxygen I can find out from MnO2, number of moles of MnO2, and MnO2 I can find out from I2, and I2 I can find out from thiosulfate. I2 I can find out from thiosulfate. Okay.
Yeah.
So if you notice, the thiosulfate and oxygen ratio is 4:1. Okay. So from the number of moles of thiosulfate, I can directly find out the number of moles of oxygen in that sample of water that I have taken. Okay. So at the end of this step, I came to know the number of moles of oxygen, and volume of oxygen we already know because we have taken a specific volume of oxygen for the treatment for this entire process. So this will give you the concentration of oxygen. Okay, is this clear, everyone? Any questions so far?
Yes, sir.
Anybody did not understand anything so far? Okay. So this is the process that I do on day 0, and I find out the concentration of oxygen on day 0, and I repeat the same process on day 5. Okay, and that is the concentration of oxygen on day 5. When I subtract the two, I get the biological oxygen demand, BOD. But remember that this BOD has to be in ppm. Okay, so how do I now we'll learn how do I convert the, because from the, if I subtract the oxygen concentration of day 0 and minus oxygen concentration on day 5, I will get the oxygen concentration, the BOD in mole per decimeter cube. The answer that I will get here will be in mole per decimeter cube. But how do I convert that in parts per million? As I said, that you need to just convert into milligram per decimeter cube. Okay, and milligram per decimeter cube is only parts per million. Now we'll see how do I convert mole per decimeter cube to milligram per decimeter cube. Okay. First of all, I will see here. You may notice here that the difference between these two units, mole per decimeter cube and milligram per decimeter cube, the decimeter cube part is same. I don't have to do anything to do with the volume part. I only only need to convert the moles into milligrams. So whatever moles of oxygen I get here, I only need to convert into milligrams. So how do I do that? I can first convert moles into gram. How do I convert moles into gram? Oxygen अगर है तो how do I convert moles into mass? Molar mass. Molar mass is 32.
Molar multiplied by molar mass.
Yeah, multiply by 32. Now, whatever is the answer here, suppose this is x. Okay, so x multiplied by 32. And then I need to convert grams into milligram. How do I do that? What is the conversion? Huh? Nobody knows.
Multiply by 1,000.
1,000. Okay.
Yeah.
So what do I do for moles to milligram directly?
By 32,000.
Yeah, multiply by 32,000. So this will be 32,000 x milligram per decimeter cube, and this will be 32,000 ppm. 32,000 x, sorry, ppm. Okay, so whatever answer you get in mole per decimeter cube, multiply by 32,000. But here I have shown you directly, but in the exam better show that conversion, like show this conversion. Yeah. Okay, now the answer will definitely not be tens of thousands that way. The answer, your answer will be like more than between 0 and let's say 5, 6, 7, 8, like that. So 0 to 7, 0 to 8, this is the range of the answer that you get, because the number of moles you get is very small value. That's in the range of 10 raised to minus 4, 10 raised to minus 5, that way. Okay, so 32,000, when you multiply, you will not get a very large value. In fact, you will get a less than 10 value. Okay, so whatever answer you get here, that you convert into ppm, and that is the BOD, that is the biological oxygen demand. Okay, now you can also categorize or rate the quality of the water body. So there are certain criteria given, like for example, if it's less than 1 ppm, okay, then the quality of the water is very good. Okay, and up to 5 ppm is accepted. So up to 5 ppm you can say that it's unpolluted. 1 ppm is excellent. Okay, but up to 5 ppm is also accepted. Above 5 ppm it will be polluted. If the demand, if the consumption over 5 days is more than 5 ppm, then it is not a good quality water body.
So what about distilled water?
Sorry, what about?
So distilled water.
Distilled water, we'll not check the BOD in the distilled water, because distilled water does not have microorganisms, and in fact distilled water will not have oxygen in it also. If it's a freshly made distilled water, it will be pure H2O. Okay, distilled water is supposed to be pure H2O. Yeah, and we also know that depending on the temperature, some of the water molecules will dissociate into H plus and OH minus ions. So distilled water will only have H2O molecules, H plus ions and OH minus ions, nothing else.
Yeah.
So this doesn't apply. This entire method doesn't apply for distilled water, and it doesn't make sense also to carry out this process for a distilled water. This is for the water body where there is life. There are fishes, there are microorganisms, there are plants, etc. Like a pond or a lake or a river, etc. No, for the distilled water, this doesn't make sense. So this question number 14 is on the same basis. Like whatever we just learned, it's the same process is given here. You need to refer to those equations. Okay, and eventually you'll find the BOD in ppm. Okay, any questions here?
No, sir.
Okay.
No,